Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science, and in this video we're going to do an example of a triple integral using spherical coordinates. So here we want to evaluate the integral where b is the unit ball centered at the origin. So what that means is that b is actually x squared plus y squared plus z squared is less than or equal to 1. So the entire unit ball and everything inside of it. Like a three-dimensional version of the unit disk, basically. Okay, so we have the triple integral over the region B, the unit ball, of x squared plus y squared plus z squared dv. And remember, dv just means dx, dy, dz, or maybe some other arrangement of these three here. So how do we do this using spherical coordinates? Well, we're going to want to make the spherical coordinate change of variables, which says x is rho sine of phi times cosine of theta, y is rho times sine of phi times sine of theta, and z is rho times the cosine of phi, and also x squared plus y squared plus z squared equals rho squared. So basically this is sort of like a three-dimensional version of polar coordinates, where rho now takes the place of r, and instead of just theta we have theta and phi. So what do these all represent? Well, let's go ahead and draw a picture real quick of something in 3 space. So we have three-dimensional space here, and this is a standard way of drawing that. So here's the x-axis in the positive direction, y-axis in the positive direction, z-axis in the positive direction. Now, rho is pretty much what you'd expect. It's the radius. So if we have a point just sitting out here, rho, let's go ahead and use a different color. Maybe a still different color. Okay. So rho represents the distance here. Here's rho. Okay, and what about theta and phi? Well, so they're both angles, theta and phi, and theta represents the angle you'd expect. So if we were to drop a perpendicular from this point up here down into the xy plane, that would hit somewhere around here, and then we'd have this going here, then theta actually represents this angle right here. This angle is going to be theta. Okay, so theta actually represents pretty much the same thing that it does with polar coordinates, the angle that is made with the positive x-axis. Okay, and remember, rho is this distance right here. That's rho. Okay, now what about phi? So rho and theta kind of still represent the same thing as r and theta in polar coordinates. What about phi? We have this new thing, phi. Well, phi actually represents the angle made with the positive z-axis. So this right here is phi. Okay, so phi is our new thing. Now, if we want to get the entire unit ball, what are we going to have to do? Well, the entire unit ball, we need to have bounds on rho, on theta, and on phi. So rho and theta are pretty much exactly as they are with polar coordinates, so we would expect, if we want everything in the entire unit ball, that's the ball centered at the origin with radius 1, then we would expect 0 less than or equal to rho, less than or equal to 1, and maybe 0 less than or equal to theta, less than or equal to 2 pi. Just like we would have for the unit disk in polar coordinates, and that's actually true. That's exactly what we would have. Now, what about phi? Phi is a little bit trickier. So imagine phi, we might expect, okay, phi is also an angle, so we want phi to go from 0 to 2 pi. But that's actually not quite right, because if phi goes from 0 all the way around to 2 pi, we're going to end up double counting some stuff, okay? Because if we think about having a unit ball here, so rho going from 0 to 1 is going to give us the entire radius. So rho is going to sweep out every radius that we have from 0 to 1 as we move throughout the unit ball. And then theta goes from 0 to 2 pi. So theta sweeps out everything in this direction. Now the problem is, if phi also goes from 0 to 2 pi, then we're going to sweep everything out twice. So what we actually want is to just have phi go from 0 to pi. Okay? So rho goes from 0 to 1. Theta goes from 0 to 2 pi, and then we want phi to go from 0 just to pi, okay? Just from 0 to pi, because then that is going to give us the entire unit ball in 3 dimensions there, okay? And remember, if if phi goes from 0 all the way to 2 pi, we're going to end up double counting this stuff that's already been accounted for by the fact that theta went to 2 pi, okay? So because theta is taking all this back here, phi going from 0 to pi already handles that for us. Okay, so we don't really have to worry about phi going from 0 to 2 pi. And in fact, if we do that, the answer will be incorrect. So 0 is less than or equal to phi is less than or equal to pi. And these are the bounds of integration now. Now, how do we change with, or how do we change into spherical coordinates from x, y, z? So here, we already mentioned these. And don't forget x squared plus y squared plus z squared is rho squared. And we also have to change dv. So dv is rho squared times sine of phi times d rho, d theta, d phi, where we might possibly have a different arrangement of these three. But for this problem, this is totally fine here, because we actually just have constant bounds on all three of these. Okay, so we're in good shape there. So then the integral, the triple integral over b of x squared plus y squared plus z squared dv equals, so we're integrating d rho, d theta, d phi. So this is this corresponds to the inside integral, this is the middle integral, and this is the outer integral. So phi is the outer integral, and phi we have the bounds of 0 to pi. And then for the inner integral, we have theta, so that's 0 to 2 pi. Or sorry, that's the middle integral. And then for the inner integral, we have 0 to 1, because that's for rho. And then x squared plus y squared plus z squared, remember, that's just rho squared. And dv changes to rho squared times sine of phi d rho, d theta, d phi. So we have rho squared, that's another rho squared, it's different from the one that we get from here. Sine of phi d rho, d theta, d phi. Okay, now let's go ahead and go, I think we actually have to go to page 4 now. Let's go ahead and evaluate this. So we're going to get, let's go ahead and rewrite what we have. The integral from 0 to pi, integral from 0 to 2 pi, integral from 0 to 1 of rho, well actually we have rho to the 4th, let's go ahead and just write that, rho to the 4th, sine of phi, d rho, d theta, d phi. And notice how we can actually separate everything here. Okay, the rho to the 4th can be kept completely separate from the sine of phi, and the theta can be kept separate from everything else too. So this is actually equal to the integral from 0 to pi of sine of phi d phi times the integral from 0 to 2 pi of just d theta, and then times the integral from 0 to 1 of rho to the 4th d rho. Okay, so this is minus cosine of phi evaluated from 0 to pi times, this is just going to be theta evaluated from 0 to 2 pi, and then times 1/5 rho to the 5th evaluated from 0 to 1. So here we have cosine of pi minus cosine of 0 times, this is just plain old 2 pi minus 0, and then times 1/5 times 1 to the 5th minus 0 to the 5th, technically. All right, now just a little bit of simplification, and we're pretty much there. So we still have a minus sign out here, and cosine of pi is -1. Then we have minus cosine of 0. Cosine of 0 is 1, so we have -1. And then 2 pi is just 2 pi. And then here we're multiplying by 1/5. 1 to the 5th is 1, 0 to the 5th is 0, so this is 1 minus 0, which is just 1, so that's all we have up here. And negative minus 1 minus 1, so this in here is -2, multiplied by the -1 out here, and that's going to be +2. So we have 2 times 2 pi times 1/5. So our final answer then is 4 pi over 5. Okay, so this has been an example of using spherical coordinates to evaluate a triple integral, and I hope you found this video helpful, and thank you for watching.